This next video is going to walk you through how to actually go from rectangular two-dimensional vectors to polar coordinate two-dimensional vectors. So it's a way of going back and forth. Now, if you can find this page in your little workbook, I don't remember what page it's on, but it's called Phys Job Composition Classics. This was all made by a nice man that's in California. His name's at the bottom of the page. Dean Bard is his name. So props to him for making this. It's really nice because it uses this grid paper to actually walk you through how to do most of the math. The example problem is given to you if you just want to read it for yourself. It walks you through how to do it with A, and I'll more or less do a very similar thing. So if I'm to just make you recognize that if you consider any random vector, R is typically used. Eventually, you're going to get into something called the unit circle, and R would be the radius of the unit circle. So often we use R to represent our basic vector. So again, this vector could be a displacement vector, it could be a velocity vector, it could be a force vector, it could be a momentum vector, it could be an acceleration vector, it could be an electric field vector. Those are all just things to consider for later. Every vector R can be represented in terms of an X value and a Y value. And every vector that is being represented as an X value and a Y value can be found by representing in polar coordinate versions, which involves the hypotenuse and its angles. So if I'm to remind you of your basic triangle shapes, this part right here is called the hypotenuse, which I usually abbreviate just hype. The portion along the x-axis is typically called your adjacent side. It's not necessarily only going to be the x-axis. I call it the x-axis because I'm currently measuring my angle from the x-axis. And so that would be my adjacent side. And this side right here that opens up opposite of my actual angle is obviously called the opposite side. Okay, so this is assuming that we are measuring our angle from our x-axis. If I measure my angle from my y-axis, I'll just draw this nice and sloppy. I'll use my other angle phi. So, and here's basically why we call it rectangular coordinate system. If I retrace this vector poorly because I'm not measuring it, this would be the same r vector in the x. This would be the same component vector r in the y. So if I actually can complete this, it does make an overall rectangle. And the only reason why I'm drawing this all, the hypotenuse is the same. It's just if I'm measuring from my y-axis, my adjacent side is now this y-axis. So I'm going to color coordinate for a reason. Right? My opposite side would be opposite of this angle, basically what I open up to. That is now technically my x-axis. And the hypotenuse remains the hypotenuse. So I did say a moment ago that typically your adjacent side is going to be your x-axis. That's not always true, but if we're keeping life as simple as we possibly can, I always find it's easiest to represent all our vectors from the x-axis. So just as a little bit of a disclaimer. So hopefully you've seen this before, and then hopefully you've seen some of the actual trig representations. So again, I'm hoping you've seen the Pythagorean Theorem, c squared is equal to a squared plus b squared. And I'm hoping you've seen SOHCAHTOA. So SOHCAHTOA, I think, is what they taught in your math classes. SOHCAHTOA, and if you've never seen this before, well then congratulations, it's the first time. And that just tells you how to write out your sine, cosine, and tangent equations. So SO stands for sine, oops, see, that looks terrible. Sine of whatever angle theta. So I'm being very specific to theta here. I guess I should color coordinate with red. Should be equal to your opposite side divided by your hypotenuse. And so that's just giving you the ratio of triangle and angles. Your ka would be your cosine, so COS, cos, as some kids like to call it, of that angle should be equal to your adjacent side, often the x, divided by the hypotenuse. And the last one, which I'm writing kind of sloppy for that, I'm sorry, would be your tangent function. So tangent of that angle is your opposite side, often your y, divided by your adjacent side, which is often going to be your x value. So those are things I hope you've seen before because we're going to use them moving forward. So keep in mind, reminder from the last video, This vector here that's in front of you can be represented in polar format, which is just the magnitude of the hypotenuse at some angle degree. So in this case, it's 37 degrees, or you can represent it in terms of its x value, comma, y value. So that would be your component form, aka rectangular format. So you have a work page that looks like this. And again, that was the one that was defined where they went through how to do I'm going to just do a random vector h. So I have a random vector drawn here, which I call h. It is 4. So from this little spot there, it is 1, 2, 3, 4 units to the left. So if I were to draw a vector arrow, I'd draw it 4 units to the left. And starting from this point right here, it is 1, 2, 3, 4, 5 units down. So that's what it is in rectangular format. It is in quadrant 3. So remember your quadrant system. I'll use green. This is quadrant 1. This is quadrant 2. This is quadrant 3. And over here is quadrant 4. I'm in quadrant 3, so both my x and my y need to be negative values. But this one's given to you. You don't really need to understand that at the moment. What I need you to do is I need you to be able to represent the same vector in terms of just the hypotenuse and some angle. So this is going from rectangular format into polar coordinate format. So I would start off by doing Pythagorean Theorem. So once again, Pythagorean Theorem says you've got c squared is equal to a squared plus b squared. Now that's the generic math formula. In physics, I'm going to call this h squared is equal to hx squared plus hy squared. And I'm using h because this vector is called vector h. So it's still the Pythagorean theorem. It's just called something different as far as the letters are concerned. And also in physics, we often start off by taking the square root of everything. So technically, you actually just have h is equal to the square root of hx squared plus hy squared. So don't let that scare you. It's still the Pythagorean theorem. I'm going to scroll down a little bit, and this is when we start to plug in our numbers. So this part stays the same, h stays the same. What changes now is I put in my negative 4.0 meters. I'm going to have to square that. I'm going to have to add my negative 5.0 meters, and I'm going to have to square that. Often I don't include my actual negatives when I do Pythagorean theorem because typically when you square them, they just turn back to a positive number. So case in point, 4 meters squared is going to negative 4 meters squared is now going to be 16.0 meters squared meters is what I should have said. And negative 5 meters, if I square that, I should get a positive 25 squared meters. So in other words, you should have no negative numbers while you're doing Pythagorean theorem. All right, add those together. I'll scroll down again. Add those together, you'll get the square root of 41.0 meters squared. So it's important that square sticks around, right? This guy needs to stick around. It's for the unit. So when I take the square root of that, square root of 41 will probably give me somewhere around 6.5. Let me just quickly do that. So you'll get 6.4 and some more change after that. But I'm just going to write down 6.4 meters. Your hypotenuse, in other words, your resultant vectors, as this is called, will always be a positive value. This guy should never be a negative number. It's always going to be a positive number. So that's just the magnitude. So over here, I would write that down. That goes into this portion. So this will be my 6.4 meters. I've already got meter written down, so I'll just add 6.4. And now I need to find the angle. Now I have this set up for polar coordinate version. I'll write this answer down 2 different ways. I believe the instructions are just to write it in polar coordinates. So next we have to figure out the angle. The angle is found from the tan function. So the tan function says tan of any angle theta. So I'm talking about, I'm going to erase this in here, talking about this right there. That's going to be that angle. Should be equal to your opposite side divided by your adjacent side. If you always measure the angle from the x-axis, then that translates into, in this case, hy divided by hx. So h because that's the vector name that we're talking about, but as far as you're concerned, it's just your y divided by your x. Now we specifically want to find the angle theta. So your calculator actually has to take the tan inverse function. So if you do that to both sides, you get the tan inverse function of the y divided by the x. And so now it's just a matter of plugging the numbers through. Make sure that when you do this, your calculator is set to degrees and not radians. If you use radians, you're going to have a bad time. So I often don't plug my negatives into this. I just do the actual pure math. So it's 5 meters divided by 4 meters. The units should cancel out altogether. If you do the inverse function of 5 divided by 4, do 5 divided by 4 first in your calculator. And so you'll probably get something like 1.25 if I'm not mistaken. And then if you take the inverse tan function, take the inverse function of tan 1.25. Don't round off whatever you get as a result here. Keep the whole number in your calculator. Press second or shift or alt. I don't know what your calculator would have, but in order to the inverse tan function, you usually just press shift, for instance, or second function, and then just press the regular tan button. You'll notice it says tan -1 above the tan button. It'll say sine -1 above the sine button. It'll say cosine -1 above the cosine button. And if you actually do this, you'll probably get an angle of 51.3 something degrees. I stop at 3, that's good enough for us. Now, you'll be tempted to write 50, oh, what happened there? You'll be tempted to write 51.3 degrees. Don't. I say that because recognize that the angle they gave us is the angle that's being measured from my x-axis going down to where my angle y vector is. So if I wrote that down in navigator method, I'd write it down as 6.4 meters. Then from my west axis, right, this is my west axis, I am going down, what was that number? 51.3. I'm just going to simplify and call it 51. Degrees towards the south. That's what I write down if I was doing my navigator method. So for the most part, a lot of students like the navigator method because we don't have to think anything past whatever our calculator tells us. We just have to think, okay, what axis am I starting from? What axis am I pointing at? And that's kind of how that's written out. But as far as writing it down in Cartesian coordinate system, keep in mind with Cartesian coordinate system, this is getting a little messy over here. I'm going to erase. We deal with our quadrant systems. This would be 0 degrees. Up top would be 90 degrees. Just ignore the B. Over here where west is, this would be 180 degrees. So if I'm in quadrant 3, I have to take whatever my answer was from the calculator and add to it 180 degrees. And that'll give me the correct angle in quadrant 3. And in this case, that's going to be 50, and 180 is 231 degrees. And so you'll have to do that in quadrant 3. If you happen to be in quadrant 2 as your final answer, if you happen to be somewhere up here, take whatever your value was that you got from tan and add 90 to it. And likewise, if you're in quadrant 4, if you're in this section here, this here is going to be 270. Just add your answer to 270. So you've got a handful on this page. You get to do A was done for you. You can do B, C, D, E, F, and G. They shouldn't take you too long. If you're basically doing the same thing over and over and over again, your angles tend to be the part that's going to trip you up the most, because if it's in quadrant 1, you can just take it face value. If it's in quadrant 2, you add 90 degrees to it. If it's in quadrant 3, you add 180 degrees to it. If it's in quadrant 4, you add 270 degrees. So hopefully you'll remember that and that you shouldn't have too much of a trouble. All right, the last little bit, I'm sorry there's lots of math involved, but that's kind of where we're at with physics now. On the flip side of that page, you'll see another one of these little circles, which basically asks you to go from polar coordinate system into rectangular system. So in other words, if I use my example H, so again, I'm using an H value. So there's H. It's a different vector on this page. So on this page, H is starting from the very center, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It is 13 digits long. So H, I'm going to call 13. I'm going to give it a 0.0 meters. I could have called it a velocity. And the angle So again, I'm in quadrant 3 again because I'm not original, so that's what I'm using this time. So there's 0, 90 is up there. Remember, this is 180. It's not represented for some reason on my slide. And all the way down here is from 180, we've got 190, 200, 210, 220, 230. This is 240 degrees. So I've got 13 meters at 240 degrees. If I were to write it down in the navigator method, it'd be 13 meters. Oh, not sure what happened there. 13 meters from my west axis, 10, 20, 30, 40, 50, 60. I could have just did that in my head. 60 degrees towards the south. Both of those are absolutely fine. I'm going to stick with this one up here, and that's what I'm going to work forward. So I want to write this down in terms of an x value and a y value. So now I have to use trig functions. So remember, I always solve for my x first for some reason. Well, probably because it's written first. So cosine of any angle is going to be equal to the adjacent side of the triangle divided by the hypotenuse side. Now, right away, you're going to go, what triangle? The red vector that you see to your right on the screen is a combination of its x value and its y value. And we make a nice right angle triangle. So this is my hypotenuse. This here is the angle that I'm using. This is going to be my adjacent side, and this here is my opposite side. So if I can visualize the triangle, I can see that my opposite side should be longer than my adjacent side. I only point that out because occasionally students will get adjacent side and opposite side backwards when they're doing their trig functions. So what I'm looking for is my adjacent. And that'll give me my x. So my x is my adjacent. I'll put an x there. My opposite side is my y, and h is my hypotenuse. So if I rearrange this equation, you don't have to memorize this, but if I rearrange this equation, my adjacent side is going to be equal to, in other words, I'm bringing this guy up top, my hypotenuse times cos of whatever my angle is. So in this case, my hypotenuse is, of course, I'll write that down on the next line. My adjacent side is hx. This is how I normally write it in class. My hypotenuse is just h, not because h for hypotenuse, but h because I'm using h as my symbol, times cos of whatever my angle is. So in this case, I go 13.0 meters. I'll multiply it by cosine of 240 degrees. So that's what I plug in my calculator. My calculator would probably spit out, I'll write this step down, 13.0 meters. My calculator would spit out cos of 240 is probably negative 0.5 if I'm not mistaken. All right, and so whatever your calculator spits out, just use that whole value. And in this case, we've got a multiplication, so 13 times negative 0.5. My x value, my adjacent side, should be negative 6.5 meters. So that's my x value. So where I see hx, I'm going to replace that with negative 6.5 meters. If you used your navigator method and used 60 degrees, suppose you plugged 60 degrees into here, the only difference between that and what I did is it'd give you a positive 5 and you'd solve for a positive 6.5, which means you'll have to use your head to remember that we are going to the left, and anything to the left of your origin on your x-axis should be a negative value. So I don't really care which one you use. If you use 240 like I did, you don't have to think. It'll just spit out a negative value, and that's great. If you decide you want to use the 60 degrees from your navigator method, that's also fine. You just have to remember that that means we're in quadrant 3, and so therefore I have to remember to plug it as a negative 6.5. Okay, my y value. So that would be my opposite side. I'll use green this time. My opposite side. So coming from my sine equation, sine of any angle is equal to my hypotenuse. Oops, my bad. Is equal to my opposite side divided by my hypotenuse. So if I bring my hypotenuse up here, I create an equation for my opposite side. My opposite side is equal to my hypotenuse times sine of that angle. So in this case, my opposite side is my y value. My hypotenuse, of course, is h because that's what this vector is called. And of course, sine of whatever my angle is. So in this case, I've got the same 13.0 meters. So your hypotenuse should be the same as your x value. In this case, I've got sine of 240 degrees. So if you plug that through your calculator, I'm just going to keep writing across. You should get 13.0 meters multiplied by probably 0.866, and then it goes on. Whatever it is in your calculator, forgive me, I'm just going to write down the first three. Keep that whole value in your calculator. Don't hit erase and then just only write down 0.866. Keep that whole value in your calculator. Do that math and you will probably end up with, oops, I goofed. It's not 0.866. Sorry, I did that in my head. It's negative 0.866. My bad. Again, use sine 240. In my head, I use 60 degrees. So that's why I wrote it down as a positive. Plug in your values, multiply through 13 times negative 0.8660. I forget the rest of the numbers. You should get negative 11.26 something or other. We'll just call it 11.3 meters. I'll just keep one decimal place for this example problem. And so now that I've got my y value, I can plug it into my actual answer up here. So my rectangular format is going to be negative 11.3 meters. So what that means, let me erase this a little bit. Let me erase this here. So my actual vector of 13.0 meters along my hypotenuse is 6.5 meters to the left and 11.3 meters downwards. And that's what it means in rectangular format. Finding out what it is in terms of x and y. I hope this was helpful. I kind of expect you to be able to go from polar format to rectangular format and backwards. As a friendly reminder, don't forget about these basic equations. Right? You've got your trig functions. I usually write it down like this. Often, this is my y, this is my x. It's not always going to be the case. And then usually I use my theta value as tan -1. Again, this is often y divided by x, but I'm sure at some point it won't be. You can probably get away with using that most of the time. Your Pythagorean theorem is often written down in terms of whatever the vector is. So in the case that I used, that ended up being h. Sometimes it might be a, sometimes it could be q, sometimes it could be z. So just be familiar with that. But it's always in terms of some x value and some y value. I will stop there. Do the 2 pages that I kind of walked you through example problems on, and you should probably not have too many issues while completing your assignments. And if you have any questions, do email me and I'll get back to you as quick as I can.